what we really want is to create a new schedule where every statement starts as soon as its data dependencies are available. Or put another way, we want to map each statement instance in the first loop in these loops into a new fused loop nest where the iteration that that statement happens in is the first one where all of its dependencies are finished. And so just to formulate this as a constraint solving problem in polyhedral style, we're going to start by describing all of the statements that occur in this program mathematically as sets of statement instances. So for example, the producer statement has 6 instances, from numbered 0 through 5 inclusive, and the consumer statement has 3 instances numbered 0 through 2 inclusive. And the data dependencies between these statements are that the jth instance of the consumer has to execute after the 2jth instance of the producer and the 2j plus 1th instance of the producer, because of course the cth or the jth instance of the consumer reads br2j and br2j plus 1, and because the producer is a pointwise operation, br2j is produced at time or at producer 2j and so on. And to represent the schedules or the loop iterations where the new instances of consumer and producer statements happen, we're going to use standard polyhedral affine schedules. So the schedule for the producer is going to be that the ith instance of the producer happens at time some parameter qp times I plus d, and the schedule for the consumer is similar. And these q's really represent the issue rate, or how often things are scaled in time. You can think of them as the initiation interval when we're working with the inner loop of a loop nest. And the D's are how many loop iterations you wait until you execute. So as a constraint problem, what we want to do is minimize the time between production and consumption of values, subject to the constraint that for all I in 0 to 2, basically for all instances of the consumer statement, the consumer statement loop iteration is after both of its data dependencies. Now we're going to restrict SC and SP to be monotonically increasing, so we can actually delete all but the last constraint, right? It actually, because if SC happens after 2j plus 1 and SC and SP are monotonically increasing, then SP of 2j plus 1 is greater than or equal to SP, which implies this inequality. So expanding the definitions and just rearranging a little bit, we can regroup the terms into this affine form, which is the issue rate of the consumer minus 2 times the issue rate of the producer times j, plus this constant has got to be greater than or equal to 0 for all instances of the consumer statement. Now this is still intractable because we have a nonlinear term here, the qc minus 2qp multiplied by j, and we also have a universal quantifier, so this isn't quite an ILP formula yet. So what we're going to do is actually strengthen the constraint by assuming that the loops are unbounded. We're going to remove the 0 to 2 constraint, and what we're going to be left with is this statement for all j, and then our affine form. And it turns out that it's just a basic law of linear algebra that for all j, regardless of the value, this could only be true if qc minus 2qp is equal to 0, and then this term dc minus qp minus dp is greater than or equal to 0. And if you're familiar with synchronous data flow, we're actually now solving a synchronous data flow problem. And basically these two different constraints correspond to guaranteeing that the data production rates match and making sure that the consumer starts after the producer. And these problems are extremely simple. They're so simple it's almost, they don't deserve to be called ILP problems in some ways, because QC plus QP is really just a problem that can be computed using least common multiple computation. And this problem is actually a difference logic problem that could be solved in polynomial time. And our solution in this case is going to be that the consumer is going to execute the consumer statement instance j is going to execute at time 2j plus 1, and consumer instance and the producer statement I is going to execute at time I. And putting these into a loop nest is a little bit of a tricky operation, though it can be done for you automatically by a tool like ISL. And basically what we're going to say is if I mod the rate at which the producer is issued, which is 1 equals 0, and if the current loop iteration is greater than or equal to the delay, which is 0, we're going to execute statement pi minus delay divided by rate by q. And similarly for the consumer statement, so for the consumer statement, the delay is 1 and the rate is 2, or the relative issue rate is 2. So our guard is if I minus 1 mod 2 equals 0, so basically every other loop iteration, and I is greater than or equal to 1, which is the delay, then execute C of I minus 1 divided by 2. And that's going to be our formula. we can actually simplify these expressions a lot and compute loop bounds and get the following statement, which is our new optimized program that will go into the scheduler. And this procedure generalizes to multiple dimensions in a straightforward way. You basically just, at each level of the loop nest, project away every other level, solve this rate matching problem, and then at the end, and together all of the conditions you got at each level to form the guard condition for any given statement. And then there'll be one loop level in the fused loop nest for each loop level in the loop nests of the input program. So that's the basic idea of this procedure. And in the next video, we're going to take a look at the quality of results this procedure produces and how well it scales compared to an off-the-shelf polyhedral scheduling algorithm. So I'll see you guys later.